who are absent can watch it as well. So Monday we did the magnesium oxide lab. We were running right at the end of class, so we kind of weren't able to finish that right away. And so we worked on it yesterday during class, so I'm not going to give any more class time besides what I'm going to do right now. We did need to grab 3 other groups and kind of look at their data as well. But then we were going to look at what happened to the starting amount, the ending amount. There was one question with number 2 here. Question number 2, we need to look at the periodic table. What is the mass of magnesium? And then what is the mass of the product? Well, the product is up here. We talked about that already. So all you have to do on a periodic table is just look at the mass numbers. And the product is 2 elements. Add those 2 masses together for that, okay? All right, now question number 5 with a scatter plot for your data. And so I want to make sure we're all good with scatter plots real quick. And so all you need to do is make an XY scatter. But again, it's really important to kind of know your different types of graphs that you guys have. Okay, so you have your X and your Y. And again, if you go back to the actual table here, you have your X and your Y already. Starting amount, ending amount. Okay, so starting amount, and then your ending, your product. And of course, these are all going to be in grams because that's what we had our balance there. And then we start off with 0, and most of you had at most like 1.5 grams or something like that. So what you might want to do, you might want to do like 0.2, 0.4, 0.6, 0.8, 1, 1.2, something like that. But whatever you do, anytime you do a scatter plot, you need to make sure your jumps are the same every time. Okay, so don't do 0.2 and then 1 and then 1,000 and then 0.5. That doesn't make sense. Okay, the ending product, you can kind of do something very similar because it didn't change a lot, but it did change a little bit. And the whole point of this is to find those patterns. Okay, on it. So for a scatter plot, all you're going to do is go up and just put a dot. You're not going to connect the dots. So I'm just going to make up some examples here. So at 0.4 might have been like over there. 0.6 might have been up here. I don't know. 0.1 might have been way up there or something like that. Let me just make up some dots here, okay? Then the next goal is to do a line of best fit. A line of best fit is not connected dots. Okay, it's not an up and down roller coaster ride. Line of best fit is drawing a straight line that tries to hit as many dots as possible. Okay. Now, if you can go through the origin with a line of best fit, you should try to do that. Okay, especially in this case, because if you start with 0 grams of reactant, you're obviously going to get 0 grams of product because you start with nothing, you're going to get nothing, right? So if we could do the line of best fit, and again, I'm going to try to draw a straight line. That's horrible. That's not even close. Sorry. Nope, don't want to do that button. Can I do this button? Nope. All right, anyway, that is not even close to a line of best fit at all. And again, that's why I don't like doing it digitally. But if you guys have a piece of paper, notebook, you guys can get out a ruler. You got a ruler, and you just try to draw a line that hits as many dots as possible. Again, that's a horrible line, okay? I'm sorry. But that is a line of best fit, is where you try to hit as many dots as possible, but you're not connecting the dots, okay? It's not making the boundary. That is a line graph. Okay, so a line graph is a graph that goes like this, okay? That's a line graph. Okay, a scatter plot. Who came in here late? Let me fix my attendance. Okay, well, if you came in late, let me know. All right, that's a line graph. A scatter graph is just where you put scatters, you put dots. Okay, that's a scatter graph, a scatter plot. Most graphs that you're going to do in real life are probably going to be scatter plots, not necessarily line graphs. Line graphs show a relationship, kind of there. So once you have a line of best fit, then you can interpolate, you can say, well, okay, well, what happened at 0.7? Okay, when you have a line of best fit, you can do interpolation. That you know, you late. So you can do interpolation, and that will, so you can say, okay, well, if I have 0.7 start with, I might end up with 0.9 or something, I don't know, okay? You could also extrapolate. You can say, okay, well, what if I have this amount over here? Well, again, you can kind of extrapolate that line. So again, it's not really very good. I missed my line. But you can extrapolate and you can say, well, what if I have 1.4? I can keep that line going, but then I can bring that line over here and see what happened at 1.4. So line of best fit is really, really useful for that. Okay, so you have one more question after you make that graph is line of best fit. So anyways, that's just a quick example on how to do a scatter plot. You guys just need to do it on a piece of paper, take a quick picture, and put it onto that worksheet. All right, I don't want to spend too much time because we do have a lesson for today that we want to make sure that we cover. Okay. And so for today's lesson, we're going to talk about reaction types today. And hopefully you guys can see this, okay? On here. So you guys have the note on your weekly schedule. It said reaction type notes. I want to spend, honestly, I want to spend 10 minutes on this, okay? What time we got? Yeah, I'm going to spend 10 minutes on this so that we could do most of today's work on this. I'm actually going to set a timer just to make myself go a little bit faster. I don't want to spend too much time on today's stuff. Okay. So we are getting into reaction types, and we had to get some background information on chemistry before we could jump straight into reaction types. We had to understand what are elements, proton, neutron, electron, valence electrons, ionization energy, like why are they reacting? And then now we're getting into actually doing the reaction parts. And I know it seems like it's been forever, but honestly, that's the way chemistry is. Even when you take college chemistry, there's a lot of foundational things that you kind of need to know in order to get to doing the fun reaction stuff. So burning things, everybody loves to burn stuff, and I like to play with fire and flames as well, which is why we try to do as many of the Bunsen burner labs as we can. But burning things is a chemical reaction called a combustion reaction. It typically uses oxygen and from the environment, from the air, and creates a combustion, and it creates products. There are 5 types of reactions that we're going to look at today in our activity. The probably most simplest one is called a synthesis. That is just where you combine 2 atoms to make one compound, or you combine 2 smaller compounds to make a bigger compound. We also have a decomposition. Decomposition is kind of the opposite, where you break them apart. We have a single replacement, where one element is being replaced by another element. And then we have a double replacement, that's where 2 elements are being replaced by 2 elements. Then we also have what's called combustion, which is what we just talked about. So again, I'm going to go kind of quick with this. I apologize. I just want to give you an overview. Today's activity worksheet handout, you're going to dig a lot more into this. So a synthesis reaction, or what's called a combination, you have 2 or more sub-reactants. Okay, and this is going to be important to know too. We're going to have some words here: reactants and products. Reactants are what we start the reaction with, and we make a product at the end. So it's when you start off with 2 reactants, 2 starting materials, and then they're going to combine together to make one bigger item. Okay, and so oftentimes the equation looks like A plus B will form AB. Okay, the thing to be aware of with that though is that just because you put these 2 together doesn't mean this has the same properties. Okay, the product. Again, these might be 2 elements, and you make a compound. It not going to have the same as the other one there. Okay. All right, and so this is a quick example of how we make water. Hydrogen plus oxygen make water. You can actually make water yourself if you wanted to, and It's also combustion reaction, kind of, not quite, but so hydrogen plus oxygen bring together to make H2O. Hydrogen to gas, oxygen to gas, water is a liquid. So again, you have a different substance, a different item there. So we have lots of different types here. I don't want to spend too much time on this, but so you see element plus element make compound. That's a really, really simple combination. A decomposition reaction is pretty much the exact opposite. It's where you start off with a compound, a reactant, and it's going to break apart into smaller parts. It could break apart into element plus element. It could break apart into smaller compound plus smaller compound. But you start off with one reactant, and you end up with two products or more. Okay, two or more simpler, smaller products. This is the opposite, for example. So if you have water, you can split water apart to make hydrogen and oxygen. Electricity is a really easy way of doing that. Be careful, obviously, electricity and water. But using electricity, you can actually separate the hydrogen and oxygen really simply. And you can get hydrogen and oxygen gas that way. And that's actually how early Earth got its oxygen gas, with the splitting of water, and the oxygen went into the atmosphere in Earth. Okay. So again, here is another example here, with the same example actually. So, all right, so if I have hydrogen and iodine, break apart, it's going to be hydrogen gas and iodine gas. Both of those are going to be diatomic because they are elemental form for those. All right, a single replacement. A single replacement reaction where you have one element that is going to replace another element in a compound. Okay, it's going to kick it out. We actually did this lab with a steel wool and a copper chloride. The steel kicked out the copper, you made copper, so they switch places. And so, for example, here is copper chloride and aluminum this time instead. The aluminum and the copper can switch places. So instead of being copper chloride, now you have aluminum chloride and copper. Okay, and so this is a single replacement. One element replaced one element, and they switch places. Okay, very common on there. Typically, what is going to happen there is that the metal will replace the metal, or if you have a non-metal, it will replace the non-metal. So, for example, add copper chloride plus oxygen. That oxygen will replace the CO. Actually wouldn't, but that metal is going to replace metal. Non-metal is going to replace non-metals. There's a reason why I won't actually do that. Where we at? All right. So you have another example here. You have zinc plus hydrosulfuric sulfuric acid. So the zinc is going to kick out the hydrogen, and they're going to switch places. The chlorine here, it's not going to kick out the Na, it's going to kick out the Br, because chlorine is a nonmetal, Br is a nonmetal. It's going to kick those two are going to switch, and you're going to end up with Br plus NaCl2. Okay, on that one. All right, so again, you have this idea here, they are just simply going to switch places in these reactions. When you have a double replacement reaction, it's pretty much the same idea, but you're going to have two elements that are going to switch together on that. Okay, make sure we're okay on time here. And so you have two compounds, and you're going to have two switcheroos going on. Okay, so for example here, you have lead with nitrate, you have potassium with chromate here. The lead can switch over here with the chromate, and the chromate can switch and come over here with the nitrate. And so you see here we have two compounds, make two compounds. And so we're going to have an ionic metal, non-metal, metal, non-metal, metal, non-metal, metal, non-metal. You know, two ionics, and the two metals here are going to switch places to go to the other compound. So the lead here, the metal, is going to go over here and bond up with this non-metal with the chromate, and then potassium is going to bond up with the nitrate. Potassium is going to go to the other side and bond up. It looks like everybody's switching partners here, but it's really not that difficult. All that is happening is that you have the starting, the metal, then metal. They just go like that. You know, they just switch places. That's really all that's happening there. It's not It's not a random assortment of possibilities. That's one reason why I kind of like chemistry. Well, I do like chemistry, but one reason why I really like chemistry compared to other subjects and stuff is that the options are not unlimited. It's going to make sense what's going to happen. This is going to bond up with that because they're both metal, and so chemistry is really straightforward in that. Whereas when you get to like life science and things like that, it gets a little bit crazy. If you look at this one here, you got calcium bromide, you have silver nitrate. So calcium is a metal, silver is a metal. They're simply going to switch places. So silver is going to come over here and bond up with the Br, bromine. The calcium is going to come over here and bond up with the nitrate. Okay, so they just simply switch places. Here you have iron sulfide with hydrogen chloride. It's hydrochloric acid. But you have iron is metal, hydrogen is on the left side of the periodic table. Sulfur, non-metal, chlorine, non-metal. Hydrogen and the iron are going to switch places. So you're going to make hydrogen sulfur, hydrogen sulfide. Then you make iron chlorine, iron chloride. Okay, so they just simply switch places. You got a new substance, which is what we just did there. Okay. Now combustion reaction, kind of where it gets a little bit more interesting for a combustion reaction. This is a reaction with an element or a compound that reacts with oxygen, produce light, heat, energy, and typically it would also create water and carbon dioxide as a result. Okay, and so here we have, this is octane right here. We got CH, octane. So, we got octane plus oxygen, which is basically what your car does, right? Your car uses octane, which is gasoline. Octane plus oxygen is going to give you a bunch of energy, and that's what runs your motor. That's what runs your engine. Okay. In the process, it's going to make carbon dioxide and water. If you ever watch a car run, if you like parking in your driveway and stuff, you'll see water come out of the exhaust. Water is the end product. So it makes a lot of carbon dioxide, which is also coming out of the exhaust. You can't see it though, it's a gas. But it also makes water. Water is going to trickle down on the exhaust, out the exhaust, and make a little puddle on your driveway. And as your engine burning gasoline with the oxygen in the air, okay, and then it makes energy to move your car, move your engine, move your piston of your engine, okay. But then it also makes the carbon dioxide, which is coming out the exhaust, and the water comes out the exhaust. Oftentimes, the exhaust starts to rust away. That's because there's a bunch of water in there. That can't happen. So, combustion reactions are going to depend on the amount of oxygen that are available. However, typically oxygen is always available because we live in an oxygen environment on there. So if you shut off the oxygen, you can stop the reaction. Benzene is very common. Is a liquid fuel. Benzene, again, we're going to react the 6 carbon, which is hexane. This is hexene. We're going to react the 6 carbon with oxygen, make carbon dioxide and water. Ethanol, same thing. When you burn ethanol, which is alcohol, you're going to make carbon dioxide and water. Just a lot of them. And so you see the equation when we balance it. Don't worry about balancing. We're going to balance later. But when you balance the equation, they get pretty hairy with that. So, all right. So real quick, I want to wrap this up. Reaction type. So 2 small substances join together to make a bigger substance. That is a synthesis or a combination. A bigger substance breaks apart into 2 smaller substances. That is a decomposition. When you have one atom, one element that replaces another, so A and B are going to switch places. That's a single replacement. If you have 2 compounds and A and B switch places, that's a double replacement. Then if you end up reacting something with oxygen gas to produce energy, light, and heat, that is a combustion reaction. All right, that was very quick. we're going to be talking about reactions a lot throughout the next, I mean, seriously, pretty much the rest of the year. We're going to be talking about reaction, different types of compounds. So, all right, now what I need you guys to do is our assignment for today. So if you guys would go to your weekly schedule and find your types of chemical reaction part A. And this is the document that we need to look for. Let's all go ahead and do this. I'm gonna do it with you. So go to your weekly schedule, find your assignment for today. I got an email. Let me read it real quick. Interesting email. All right. Does everybody have their worksheet up? Everybody have it? I'm gonna go over a lot of it with you. All right, so do atoms drain the period in predictable patterns during chemical reactions? So why are we learning about this? So recognizing patterns allows us to predict future behavior, which is what chemistry is all about. Weather experts use patterns to predict dangerous storms. You know, political analysts use pattern to predict outcomes for election, and chemists can use pattern to figure out what's going to happen in a chemical reaction and whether or not we need to be extra safe or all those type of things, which we should always be safe. So this is a model here of a bunch of different types of reaction. Do me a favor, when you make your own copy, fix this for me real quick. I can't fix it. This is not my document. This is Miss Hyde's document. But if you just delete that and make this all come back together, this over here should be right there. So fix that formatting for me if you get a quick chance. But this is a model of a bunch of different reactions, and we have synthesis, single, decomposition, double replacements. These are the ones that we were talking about. Combustion, not on there. We'll talk about that one a little bit later. So the very first thing we want to do is write the chemical equation to model one all have a bunch of letters with them. S, G, L, and AQ. So very first thing I want you guys to do is in this symbol, in these blanks here, which letter do you think goes with which blank? So take about 10 seconds, type in your letters into those blanks, and we'll figure out what number one is. Yeah. All right, so somebody in the chat box tell me what are the letters for dissolved in water mean? Yeah. Yep, and if you know Spanish, you get an idea of why that is water. But basically that just means aqueous. It's Latin for water, aqueous. And so AQ, goes here for water. Liquid, obviously L, solid, gas, SG. And note on there, we're going to talk a little bit more about this in a little bit about, a lot of them are pretty aqueous here. All right, based on example provided, so in these examples here, which set, A, B, C, or D, in model one typically involve ions in solution? So ion in solution. Which one typically, so solution with water. Which one of these typically involve aqueous ion? So take about 15 seconds. Look at set 1. Do you see a bunch of aqueous? Look at set 2. Do you see a bunch of aqueous? Look at set C. Do you see a bunch of aqueous? Look at set D. Do you see a bunch of aqueous? Go ahead and put it down in the chat box for me when you get the answer. Okay, I'm gonna be one of them. There could be more than one answer there. So ions in solution. Solution means it's in water. So you have a solution of something. So ions in solution mean that aqueous. So we're looking for ones that have a lot of aqueous with them. So set C, aqueous, 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 aqueous. Set C definitely. Set D, aqueous, aqueous, aqueous. There's a lot of aqueous there with set C and D. Okay, and we're gonna talk a little. You'll kind of goes in there a little bit. Talk a little more about that why in a second. All right, so based on which set typically deal with gases or solids. So again, take it 5 seconds, look at those sets, which one are typically gases and solids. And again, there could be more than one. Excuse me. Let's see what you guys got. So gases and solids, primarily here are going to be, they got a lot of gases and solids in set A as well. Solid, gas, solid. Set B, solid, gas, solids, gases. So set A and B are typically going to be involving gases or solids for set A and B. So synthesis reaction, especially, and decomposition, you make a lot of gases in them. All right, so this one said match each description below to the set A, B, C, or D. So you should only get one letter in each blank here. So it says ionic compound dissolved in water switch partners. One compound breaks into element or smaller compound. Two or more element or compounds combine to form one product. Part of an ionic compound is removed and replaced by a new element. So take a second, take a minute to think about that one. And then in the chat box, let me know what you think. Like what order is it? The A, B, C, D, the B, A, C, D. So in the chat box, when you think you got that answer, let me know what you guys think about question number 4. She'll give you guys a minute to work on that one. Did everybody agree with Dobie and Isaac on that? Dobie said ionic compound dissolve in water and switch partners. So you're looking for 2 compounds. Okay, so compound. Yeah, so set D is two compounds. They're in water, and they switch partners. Okay, so yeah, so the first one is D on that one. It said one compound breaks apart into smaller parts. So element, well, that's compound, element. One compound, smaller stuff. Yeah, so set B is the second one there. Two or more elements compound joined together. So two elements compound, two element compound, two compound and an element compound, bigger compound. And so they join together to form one thing. So they form one thing there for A. And then the final one there is replaced by an element. So if you look at these here, most of these should have elements involved. So there's an element there, there's an element there, there's an element there, element there, element there, and element there. Okay, so you have a compound and an element, and you're switching places. All right, good job. All right, number 5, I'm gonna let you guys do this one on your own. This is your own definition, but this is just kind of using them in your own words. What does a synthesis reaction mean to you? So use these sentences up here, but think about what does that mean to your own brain? Okay, what does synthesis mean? What does decomposition mean in there? So, all right. So of the 4-session reaction, have the following general name. Which name belong to the set of chemical reactions? That's the name. Okay, well that's easy. We kind of just did this here. So, wait, what are the 4-session chemical reaction? One has the following general name. Okay, so single replacement. What letter is a single replacement? What set? A, B, C, or D. What set is a single replacement reaction? What? I already had the name on it. That's what I was thinking. Like when I saw that, it seemed like it was weird. But anyways, all the answers are there for you already. Well, set C is a single replacement. That's why when I read that, I was like, that doesn't make sense. Write the name. Yeah. Anyway, so yeah, so C. A, yeah. So C, A, D, B. Okay. All right, so number 7, can two elements be used as reactant for a synthesis reaction? Can I do an element plus an element for a synthesis? So go up here, look at synthesis. Can I do an element plus an element? So in the chat box, yes or no? Can I do an element plus an element? Yeah, there are multiple examples. So using the evidence, look, I could do the two right there. Both, well, this one and this one. Those are both element plus element, make compound. Okay. The other ones are compounds, so we don't really want to use those as examples there. Can two compounds be used as reactant for a synthesis reaction? So let's go back up here to synthesis. Can I have two compounds come together? Yeah, we got quite a few examples of those. We got 3 of them. We got 3 examples of compounds coming together. But again, remember, you're gonna have 2 small compounds, and they're gonna make a big compound, a bigger compound. Okay, so that's a synthesis. 2 smaller parts make 1 big part. All right, let's go down here. What type of substances, elements, or compounds are seen as products of decomposition reaction? What type of substance, elements or compound? Decomposition. Or both. We're looking for the products of decomposition. Element or compound? Or both. We got two different answers there. Oh, we got three different answers now. Let's try to get a majority vote here. So it's going to be both here for decomposition. That was a question, right? And decomposition, yeah. So decomposition reaction is going to be both. And the idea there, it's just going to be smaller than what you started with. Okay, so look, get the really big compound here, and this is smaller than that. That's smaller than that. That's smaller than that. And so you're gonna take a bigger compound. You're gonna make it in a smaller part, and it could be both. It could be compound or element. Number 10. In a single replacement reaction, do any of the atoms change their charge? If yes, use an example from Model 1 to describe the changes taking place. Do any of them change their charge in a single replacement? Here it is right here. Do any of those change their charges? Anybody in the chat box? Do they change their charges? All right. I think how they change their charges. Give me an example of that happening. Well, they could definitely change their state of matter. I'll give you that one. But they don't actually change charges. And so they still have the same charges that they start with. Cl is still going to have a minus one charge. F is going to have a plus 3 charge. They're always going to have the same charges in a single replacement reaction. And again, that's part of conservation of matter, is that you also have to have the same charges on both sides of the equation. You can't add charges or lose charges, or you can't create or destroy charges either. Now, there are chemical reactions where you can change the charges, but you have to make sure everything stays balanced. Those are called redox reactions. But in a single replacement reaction, all those charges are still the same. Now, that question is a little bit tricky because it doesn't show you the charges, especially like copper here and iron there. But in a single replacement reaction, everything is conserved, everything is balanced. They're not going to lose those charges on there. Okay. And the same thing for 11 here. The atoms change their charges. No, they're ionics. All the charges are being balanced or kept the same on both sides of the equation for 10 and 11. All right. So it says choose one example from the set of synthesis reaction in Model 1. Write the equation in reverse. I'll let you do that. Just go up to Model 1, copy a synthesis reaction. So copy one of these and write the equation in reverse. You're just gonna move the product over on the left, okay? Now, do you guys know how to write an arrow with your keys? Oh, I can't write. I can write on this page. But if you go to write in your box and you do dash 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 dash, I guess that's greater sign. Dash dash greater sign. and you hit the space bar, it will make an arrow for you. Okay, so you just type in whatever you want, dash, greater sign, space. All right, so okay, so I'm gonna let you do that. All you have to do is just write it in reverse. Everything's gonna stay the same. Everything's gonna stay the same, so don't mess up anything. Just switch it up. All right, label the reaction written in part 1 with reaction types in model 1. So what is the opposite, what is the reverse of a synthesis reaction? That should be pretty easy. Okay, and then the last one here is based on the definitions that we did, based on the examples in model 1, there are 8 more reactions here. And the idea here is to try to figure out, is this going to be a synthesis, decomposition, single replacement, or double replacement? Do me a favor real quick and hit the backspace on that single replacement. Bring that sentence back together. For some reason, that sentence broke right there. But is it going to be a synthesis, decomposition, single, or double reaction? Again, look at the example, look at the models that were given to you before model 1. All right. We crammed in, wrapping up the graph for our magnesium oxide. Very, very quickly, rush through some notes. This gives you a little bit more practice with those notes and the type of reaction. And then, of course, we're going to spend pretty much the rest of the year talking about chemical reactions and stuff. So do me a favor, try to finish this up today, tonight. Honestly, I just did a lot with you, so you should be able to finish that up pretty quickly, maybe 10 more minutes of work. If you don't finish it up tonight for homework, we'll finish it up tomorrow during class for Thursday work. Thursday, I do want to talk about a couple little things outside of chemistry on that, and you go from there. So this is due on Friday, like most of our assignments are due on Friday. All right, so, but again, I want it, get it done, turn it in. Don't wait till Friday. Yep, no point. Because Friday you're gonna have work too. So just, get it all done when we're doing it in class. All right, that's it for me. You guys have a great day, and I will see you guys tomorrow in class. Have a good one.